Machine learning starts here, which is basically your linear regression. We first understood how do we represent a line, and representing a line or fitting a line onto some data or some data points was named as fitting a line, or finding the best fit of the line that fits the current data. And obviously the algorithm turned out to be linear regression, right? So now we have to understand from the first principles everything around this particular algorithm. Now I've taken a few examples. Let's say that x is equal to 2, right, and y is equal to 2. So, and x is equal to 4, then y is equal to 8. When x is equal to 5, then y is equal to 11, right? So we can see that there is some sort of relationship between the x and y. When x is 100, then y is, let's say, this 296. These are all the data points that are given to us, right? Now onto this data point we might have to fit a line. What will the line do? The line is likely going to represent the existing set of data point, right? Now let me just show you something around fitting a line, how basically it looks like. Okay, so we can see that there are some data points. So assume that the blue ones were the given set of data points given to you, right? Now this horizontal axis, assume that this is x. The vertical axis, assume it to be y, right? So when x was close to 1, the y was close to 6, right? 1 comma 6. The second point was 2 comma 10. The third point is, let's say, 4 or 3.5 comma 13, and so on. Now what we did was, we said we want to represent all of these data points using a line. Now can we do that? Obviously can do that. We can just fit a line or put a line on top of these data points. This data seems to have a small curve. We can always debate that whether this line is the best fit or not, right? But doing is always possible. Fitting a line is always possible on the data. If your data follows a simple linear relationship that is easy to track using a line, then obviously the line will feel as if it is a seamless thing. For example, here. But if your data here, I think we can see that it might be a parabolic curve. So here line might not make a lot of sense. Even if it is making sense, it might have some error, right? So this is what exactly is all about fitting a line. Given a set of data points, we have to fit a line. Now using this line, I will be able to represent a function which will be able to map my x to y, right? Given the x, I can predict y. How can I predict y? Because I have the line equation, right? What exactly is this line made of? The line is made of two parameters, slope and intercept, which we simply call m and c. Now let's come back here, right? Let's see. This is a line which represents y is equal to 3x minus 4, right? For example, let's say this is the given line. Now the slope of this line is m, and the intercept of this line is minus 4 or negative 4, right? Now if there are no neighboring data points, but I want to help you visualize how does prediction works. Let's assume that there were a lot of data points that this line is representing. Now that I have computed the model parameters, which are nothing but my slope and intercept, m and c, right? I've computed them. If you give me an x, if you tell me my x is 2, can I not predict the y? I obviously can. I will just plug and play in this line equation. Y is equal to 3 into 2, which is 6 minus 4 is 2, right? So what that means is when x is equal to 2, y is also equals to 2, right? So this is the classic equation of a line. The equation of a line hence also becomes the equation of a model. So the model becomes such that the model helps us predict y given x, right? Now let's again walk through what we have learned. This is how you would be given a data points. Now if you can club them in a CSV file, it will become a tabular data. One column is representing x and one column is representing y, right? Using these data points, I will plot the data points. I will produce a scatter plot. That scatter plot would look something like this, obviously without the line, right? Now when I plot the scatter plot, I will produce a line that will represent that scatter plot, right, on a visual basis. But what I'm trying to do on a mathematical basis is that I am trying to figure out a model, a line or an equation that represents my current probability distribution of the data, right? Okay, so now let's take a small real world analogy. So let's say the x is the size of the house in square yards and y is the price of the house. Okay. So, and the model that we are trying to produce is given x y or predict y, right? First, I will give a machine learning model a lot of these data points. I will give them 1000 prices of houses, 1000 prices of, 1000 sizes of houses, against them 1000 prices of houses, right? So that means my CSV file now contains 1000 house in square yards and 1000 house prices, which basically is represented as y, right? What I essentially also mean that my data points, the total number of data points that I have are 1000, right? 1000 data points. Each data point is representing two things: what is the size of the house in square yards, what is the price of the house, right, in dollars. Now what we have to do is we have to try to learn a function that maps the size to the price, right? That's what we have to do. Let's imagine that once you learn a function, you can deploy a broker, right? A broker who will answer what is the price of the house given the size of the house. The broker will get a random call, and the broker will, be asked to predict the size of the house, sorry, price of the house, right? So that means y, right? So the predicted y is also denoted by y hat. We will see in the upcoming lecture, right? So right now what we have to do is we have to predict the, or we have to model it as a linear model or as a line, right? Linear model or line can be used interchangeably here, because we might say intuitively that we're trying to fit a line, right? But all in all, what we're trying to do is we are trying to fit a linear model. Now, luckily, that linear model is represented or can be represented as a line in 2D space. But when we take it to 3D, it might be a 2D plane, right? For example, something like this, right? It is still a linear model. If I extrapolate to one more dimension, from 3 to 4 dimension, it's going to be a 3D plane or a three-dimensional hyperplane. In n dimensions, I will produce something known as n minus one dimensional hyperplane. In 2 dimensions, I will produce a one-dimensional line, right? So that's why when we are talking about the sub-problem where we only have two parameters, m and c, and one input which is x and one output which is y, then I can correlate everything with fitting a line. But when I extrapolate it to multiple dimensions, for example, something like this, right? Now I cannot call it a line. I will have to call it a hyperplane, right? Now, just imagine I am representing x1 as size of the house, x2 as maybe the carpet area. Let's say this is the super area, right? Given the size of the house, the carpet area, the super area, I have to predict the price of the house. Now this equation has three features: feature 1, feature 2, feature 3, right? The equation of the line becomes, or the equation of a linear model becomes, y is equal to w1x1, w2x2, w3x3 plus b, right? Now this equation represents that we have three features and we have something known as an output as a n minus one dimensional hyperplane or a three-dimensional hyperplane, right? It's not a line. We will produce a three-dimensional hyperplane. Now, what exactly is this? B is nothing but the bias, right? In case of a line, we called it C, right? Or basically the intercept. In case of a hyperplane, we will simply call it bias, right? That's it. So what we can understand from this, when we are talking about a specific two-dimensional plane where we only have one feature and one predictor variable, we call it a line. When we have n features and one predictor variable, we call it a linear model. Why is it linear? Do you see that there is no, higher degree than 1 of a polynomial? The highest degree polynomial is 1, right? I don't have x1 square or x2 cube, right? That's why it is a simple linear model. I have no way to measure or model non-linearity in this equation, right? It is going to produce a hyperplane. It is going to produce a line. It is never going to produce a non-linear curve, right? That's why it is a linear model, right? Now the number of features directly corresponds to your number of parameters. Since there was only one feature, which is the size of the house, that's why we only had one parameter against it, which is m, and then one bias. If I had three features, then I will have three parameters and a bias. If I have 100 features, I will have 100 parameters and a bias. If I have n features, then I will have n parameters and a bias, right? So number of input features also, translates to number of parameters in your model. The more parameters in any model, the more the model grows, or the more the size of the model grows, right? Now let's go below and try to understand. Now we will stick only to the equation of y is equal to mx plus c, right? We will not extrapolate into multiple variables, into multiple features. Why? Because we know if we can figure out something for this particular equation, we can extrapolate into multiple x's or multiple m's, right? M and x will grow with respect to the problem, right? If because we can generalize it, right? We can generalize it to as many variables as we want. So if we want to figure out how this model works, how to train this model, how to fit this model, if we can figure out anything and everything for this model, we can do anything and everything for any variable, of this model, right? So it's worth discussing this particular equation. So let's assume that this is our model equation, right? Why we have always assumed that it's going to be the predicted output. No matter what problem we discuss, whether we discuss logistic regression, or we discuss linear regression, or we discuss any deep neural network, more or less we will always correspond y with the predicted output, and we will always correspond x with the input, right? So here x is a scalar, m is a scalar, c is a scalar, y is also a scalar. Means it is not a matrix, right? It is only a single element, right? It's a 1 cross 1 element, that's it, right? So we know that whenever we talk about equation of a line, we have studied it in simple algebra, not even in linear algebra. In simple algebra, we have studied that y is equal to mx plus c denotes the equation of a line, where m is the slope and c is the intercept. Okay, makes sense. Here what we are saying is x is the input, m is the parameter that gets multiplied with x, c is the parameter that acts as a bias, y is the predicted output, right? The same linear model, the same line equation, right? Just different paradigm to look at it, right? In Hindi we say nazariya, right? So in English we say paradigm, right? We're just looking at it from a different paradigm, right? So in general, this equation represents the equation of a line in 2D space. Awesome. Okay. Now why this is a straight line, or why this defines as a linear model? Because the output y changes proportionally with x, right? That's why. Because we have a linear relationship among x and y, right? Among the random variable x and the predicted variable y, and the highest power of x, or the highest degree of polynomial, is only 1. That's why it is a simple linear equation, right? So what is it that we have to do now? We have to understand or correlate this equation of a line with something known as a machine learning model. In every machine learning model, we will have two things. One thing is we will have a model equation, right? We will try to optimize something. What is it that we will optimize? A loss function or a cost function, all right? And while we do optimize that loss function, which we are going to define in a while, we are going to call that process as the training process. The whole steps that we take to optimize this particular loss function is known as the training process. After we have optimized the loss function, we have received the best parameters, or we have received the model, then we will use it to inference, right? Inference means call it, query it, predict it, or predict from it, or inference it, right? So there are only two phases of a machine learning model. Phase one is training phase, where we train the algorithm on a lot of training data. Phase two is inference phase or testing phase, where we call or query or inference or predict using the trained model, right? All of these things can be used interchangeably. Okay, so before we understand what exactly is training, we have to first understand what exactly is the cost function here. Okay, let us formally describe the cost function. Okay, now before I describe the cost function or loss function, I want to talk about some common sense things. Okay, let us assume that all of these blue data points is the scatter plot of my available data, right? So you belong to a city known as New York. You were asked to collect 1000 data points of 1000 houses, and these data points describe, the first column is the size of the house in terms of square feet, right? And the other data point, the other column, is the price of the house, right? So you have 1000 houses, H1, H2, H3, H4, so on till H1000, right? And for each H1 and H2 and HI, you have size of the house in square feet from New York, right? Let's call that X because that is a given input, or that is something that you collected. And you have something which is known as the price of the house. Now, all of this, let's assume that you collected it manually during a survey that you did in New York, right? Now you have 1000 house prices consolidated in a Excel sheet, in a spreadsheet, right? And 1000 house prices with respect to their sizes. You want to build a model, or let's say you want to build a function, an approximator, whatever you might call it, a predictor that can predict the price of the house given input data, right? In this case, the input data was only one variable, which is size of the house, right? And you want to build an approximator or a function or a model, whatever you want to call it, a model that predicts y, a model that predicts price of the house given x or given input, a model that predicts y, right? So now let's look at it. How will you do it? You will plot all of these blue data points, right, against the horizontal axis x and against the horizontal axis y. On this xy plane, you will plot all of these data points. Now you will start to define a line, because you only are allowed to work with a linear model. You cannot, fit a non-linear model or a non-linear curve on this data, right? No matter whatever data you have, you only have permissions to plot a linear model. That's it, right? So given all of this data, you're going to plot a line. Now you start plotting a line. Let's say this is the line you plot. Now, since you are not a machine learning scientist, you are a visual learner, you plotted them on a piece of paper and you try to fit a line using your scale, using your visual learning, using your visual optics. You see some data points and you try to fit the line. Now, if I want to understand whether this line is good or not, right? How will you help me understand? For example, let's supposingly this is the line that you plotted. I want to understand whether this is the line that is an efficient line, or this is the line that is an efficient line, or this is the line that is an efficient line, or this is the line that is an efficient line, right? I need something, a quantifiable metric to define the error, right, or the cost, the performance of the line, right? Now let's say this is my line, okay? If I move the intercept here and slope here, I can see that this line is more or less closely connected with the data, right? Whereas this line is far from the data. The distance between this point, the distance between the blue point and the yellow point, is known as my cost or my error or my loss. If I cumulatively know how to add them, right, that will become my loss function, right? I hope you were able to understand a little bit. Like, whatever I'm trying to say is, I'm trying to make sense of what is it that might define your loss function. Your loss or error or cost is nothing but the distance between the true value, which is the blue dot, and the predicted value, which is the red dot on this particular line. This is your cost, right? We can also call it true minus predicted. Now, since this cost can be negative or positive depending on which side of the line are we will take a whole square of it, right? So that's why we use the square method or the sum of squared errors. So if I can define my error term, which is basically nothing but true minus predicted, or yi minus yi hat. So yi hat is nothing but denoting the predicted. Yi, because for every single data point I want to compute this, right? So true of ith point minus predicted at ith point is known as my error term or my residual term. If I can do a square of all of these residuals, so that I only take the magnitude, right? So that the negative and positive don't cancel out each other. I either have to take a square or I either have to take an absolute value. If I can do the square of all of these residual terms and then I can do a summation, it's going to give me something known as sum of squared errors, sum of squared residuals. Very self-explanatory, right? We have taken n and we have taken n residuals, n error terms, and just squared them and then added them. That's how we call it as sum of squared residuals. That's it. So this becomes our cost function. Instead of yi hat, I just put mx plus c. Why? Because yi hat is nothing but mx plus c is the equation that helps me predict and come up with my yi hat, right? So, and extrapolated from, I iterated from I is equal to 1 to n, and if I mathematically formalize it, I call my cost function as j is a cost function of m comma c that is represented as summation of I starting from 1 and going all the way till n is nothing but my total data points, total input data points or training data points, right? And yi, which is my true value, minus mxi plus c, which is my predicted values, whole square. This is nothing but my cost function. Now the intuition will go, or the storyline for linear model will go something like this, or for any machine learning model. I know what this is my cost function. The less the better, the more the worst. If I can figure out how to reduce this cost function over time, right? And figure out the best m and the best c while also reducing this cost function, right? Now, every line is defined by its slope and intercept. I just have to figure out what is the best m and what is the best c that I should use to place my line, right? That is going to help me, you know, find the best fitted line. And if I can figure out the best m and the best c such that my loss is minimized, such that my line is tightly coupled with my data points as much as it can be, right? Now loss might not always be zero, loss might be a positive quantity, right? But it has to be at a minima, it has to be minimal, right? The least it can be. And whenever it is the least, there I'll have my best m and best c, right? And I also know if I can solve it for a line equation, I can extrapolate it for any linear plane, any linear hyperplane in any n dimensions, right? So that's it for this particular video. I hope you were able to understand what is the cost function with respect to a linear model.